All right, so then let me see assignments. Okay, I have put it in discussions for a moment, and then, yeah, and then I will move it all. I left it there just in case you have any questions, you want to have any discussions with the solutions. So let me see how, I need to make sure what I put, how can I find what I have included? Okay, here. How do we see that? Okay, I will have to fix that. But in any case, I will have to upload it. I tried to do something, it didn't work obviously very well. So, but I will show you the file that I have for the solutions. And then you're going to see it uploaded next. Let me find the file here. File. Okay. Here is the solution for the homework. And in fact, I did it like this because practically it's a review also of the material we covered, all right? I don't necessarily want you to type or anything when you show solutions, but I want you to follow the process and set up your problems correctly. All right, please read the solution because it's going to help you for the following homework. The next homework is very similar to that, but focusing specifically on writing code. Because the first observation that I saw is first, number one observation. A number of students did not remember how to write code. And I think coding is part of your freshman year, and we have to use it to be able to avoid getting stuck on math, to be able to understand what is happening. So I also sent in, suggested as part of your second homework to use this collaborative website where you can write Python. But the nice thing is that you can share that with a friend or with your team who can then help you with the writing. So for example, this is how it looks on the website. This is a simple program I put together, and I'm not, I did not learn Python as a student, obviously. I learned whatever else was available at the time, Archaic, Basic, and whatever Fortran was available, and then C, and then C++, but that's where I stopped. So Python is a very powerful language, and that's how it really looks. On this one, there are some small changes with the traditional Python, but if you look at the information, how to incorporate your various functions, it's going to be easy to put it together and then do different plots. You can use the plots to find a solution. You can plot 3D as I did here. You can plot 2D. But what I wanted to show you is that you can use that to be able to develop visual solutions. All right. So the next thing that I did is to develop the second part of the problem, and I set it up in terms of potential. And then I found this very nice solution from one of you, really very professional. However, I have to say that there is one problem with that particular solution. There was no setup of the problem anywhere. Yes, the solution was correct, at least the plot. But, for us, if you find a program where you enter the position of the charges and the value of the charges, and the whole program does it for you, yes, visually you learn if you pay attention and see where is your maximum change. If you remember from the quiz that I gave you, because the electric field, let me put it here in create a new note. I would like to go there so I can write things. So if I go here, all right, then you remember from, I mean, how do you read this? You remember from the quiz that I gave you. In the quiz, there was a variation of the, let me see, excuse me. So let me write here, in the quiz that I gave you and how you translate that quiz into this one. In the quiz, I showed you a variation of, say somehow there, of the B versus X, A, B, C, D, and E. I believe A, B, C, D, and E. And I asked you at what point the electric field has its maximum value. All right. So in this particular case, according to what we know, that E is minus gradient of V, the electric field is going to have its maximum value where V has its maximum variation. All right. And for example, V has its maximum variation if you look at the lines where here, 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 all right? Maximum variation in the field here, obviously, here, wherever it changes. And then where does the field has its lowest variation? Here, all right, here, obviously, and other places like that. So the field gets its, becomes zero in the green areas, all right, practically. And the field becomes maximum in the yellow areas. So yeah, you can say, you can see it like this and get some ideas, but at the same time, I would like you to do some setting up of the problem. All right, before you just show me. I don't want to see your code, which is fine. I mean, if you want to put a code like that, okay, I can read it. I'm not going to correct codes, but I'm going to be looking at your outcomes. There are two things I'm going to be looking at the setting up of the problem, and if I ask you for a plot, and a plot. But if you only give me a plot, not the setting up the problem, and the plot is not correct, I don't have too many things to grade you on. So that's number one. The other observation that I've made is I had mentioned to I think both sections that when you upload your material, make sure, first of all, if you take a picture, that the picture is readable, that is not too dark, so I cannot see the lines from the background or clearly, especially if you write small, you type small. And then the second is, if you write with pencil and the lines are very faint already, then make sure that you process a little bit your PDF so I can see the lines, as opposed to uploading them just whatever way. And then if I don't see your solution, what grade am I going to give you? So I'm meeting with the graders for the first homework to decide how we are going to split the grade and how we're going to give you input, and then follow that for all the other homeworks. So in any case, the first thing in this homework, the highest priority, is to make sure that you remember how to plot functions so we don't get stuck in the math and we cannot see exactly what is happening. So you find it easy to write a program like that in like 15 minutes. Okay, and I know that there are students who did not know how to program, they did not know how to do it. Okay, so let's try to figure out that we remember this. And I gave you homework, second homework, exactly doing it that. So when we continue with the homework, at least you have already remembered how you do your coding. And it's not only important for the class, I think it's very important when you graduate as engineers to know how to code. I mean, engineering is that fundamental, all right? You cannot say, I don't know how to code, I don't know MATLAB, I don't know, then what, right, in that regard. Okay. This is a discussion we're not going to have in all homeworks. It's just the first homework, which I believe gave me a lot of information, so I can give you a lot of feedback. Any questions about the homework or any concerns, any suggestions? Okay, you're going to also have the solution uploaded. So today I'm going to upload all of that, which is ready, and the solution, which is conceptual, with an explanation for the solution by the end of the weekend for team homework number 2. All right. So now the next thing we would like to do is to introduce new concepts. Let me see here. My notes to the right. Okay. And there are 2 important concepts that I'm going to write them here. It is on your notes, which is module 7, and then module 8. But let me write it here. So what we have seen so far is that if we have a charge Q, and let's assume that this charge distributes at one point, it's a point charge, all right? Then we know that at some other point, if we bring a small charge Q, then there is going to be either a repulsive force on this charge Q or an attractive force. We always assume, especially as we are looking at electric fields, that this charge, which is the observer, by convention, we make little q to be positive, all right? And therefore, in this case, if we start with F, which is the force between the 2 charges, and let's assume now that these 2 are in free space, then we will have that this, if this is R vector, all right, which goes from O to A, then we have that this is equal to that, all right? And then from here, we have that E is going to be F divided by Q, and it's going to be capital Q over 4 pi epsilon naught, and then OA over OA magnet vector cube, or Q over 4 pi epsilon naught, and then it's R over magnitude of R cube. All right, where R is OA. R is OA. So this is in free space, and if it's not in free space, if this is in fact embedded in another material, let's assume that all of this, the space is all of these charges are in another material that has here dielectric permittivity epsilon. In this particular case, if that's, then that will be epsilon here, all right? That will be epsilon and epsilon. So next, we are defining D, a new vector, which is called the electric flux density. Okay, and that D is going to be epsilon E. All right. And therefore, now we define D for a point charge, from a point charge to be equal to, okay, let me change this. 1 second, so I don't lose this. Okay, so from a point charge, then D from the above equation is going to be Q over 4 pi R over R cube. Okay, so that is, as we said, electric flux density. It's density. So if it's electric flux density and epsilon, excuse me for a moment here. Let me see what are the units, all right? Think that E has the units of volts per meter. Epsilon, which is epsilon sub R, epsilon naught, and epsilon naught is the permeability of the space, is, if I remember, 1 over 36 pi 10 to minus 9, and it's farads per meter. So D, all right, has, if you see the multiplications, since it's epsilon E, is going to be in units, farads per meter times volts per meter. But also we know that farads times volts give coulombs. So D is going to have the units of coulombs per meter squared. It is a density, therefore it is a flux density too, if you noticed. It's not just we call it an it's a charge density. We don't only call it an electric flux density, we also call it has the units of a charge density, coulombs per meter squared. Okay. Now, we are defining, now that we have done this, we are defining, after the flux density, the total flux, electric flux rather. And the total electric flux, we define it as phi sub E. And how do we define that? We define the flux, the total flux, as a surface through which the flux lines are going through, so D dot ds. But to be able to show that, I will go to my notes because I have two nice figures that I would like you to see. Okay, so here I have two cases, and I'm doing this here to be able to define the electric flux, as you can see. All right, here. The electric flux is this one. I would like to define it, but to be able to define it, I will go to these two pictures that you have them in your notes, and everything I write on the side is written on this document. So we have a chart here, first of all, this one, that I have made it big enough so it seems like to be distributed, but is also centered at the center of the sphere. And then the same sphere is on the other side, on this case B, but there is no charge to it. It's just that the sphere is inside an electric field that was generated by a charge somewhere away. All right, assume that you have a charge that is far away, and inside the space where the electric field is generated by this charge, we place that sphere. In the first case, in case A, the charge that is inside the sphere generates an electric field. Assume that is a positive charge, therefore all of the lines, they will leave the charge and they will move towards the outside of the surface. As a matter of fact, we call this surface a Gaussian surface. It's a spherical surface, and many times you will see reference to it as a Gaussian surface or a Gaussian sphere. All right. And then all of the field lines that are generated by the charge, they are going through this Gaussian sphere And of course, perpendicularly. All of the lines is along the radial direction of the sphere. All right, so they go like this. As you can see, all of the pictures, all of the lines that come out. All right. Now, all of the lines also, since the electric field is generated by this charge, they initiate on the charge. All right. Therefore, not only the electric field lines initiate on the charge, but the electric flux density lines, since the electric field and electric flux density are connected through epsilon, which is a scalar, and epsilon is a constant, then whatever happens with the electric field happens with the flux density. So if the electric field lines look like this, that you see here on this graph, and they go out from inside of the sphere outside, then the same thing is going to happen to the lines of the electric flux density. Therefore, all of the lines of the electric flux density they initiate on the charge or at the charge, and then they move out. And they move out and they exit this Gaussian surface, all right? And all of them are leaving the surface. Now, if this is one observation, so they're all leaving the surface at the same time. So now, however, if there is no charge inside that surface, but there is a charge outside that has created an electric field, so for every line that goes in the surface, there is also comes out from the surface. Every line that goes in will come out. There are no lines, therefore, that terminate somewhere inside the surface. If we have 5 lines coming in that show, 5 rays of the electric field, 5 of them will come out. All the same 5 will come out. All right, that says, therefore, that there is no accumulation of line inside the sphere, because whatever comes in comes out. And this is very important because we define now the total flux phi sub e to be the surface integral of your flux density over a sphere. All right, always we consider flux density to go over in a 3D, obviously. Flux density, there are these lines that they will go through a surface. It can be a spherical surface, it can be a 3D arbitrary surface, it can be a planar surface, it can be an arbitrary, planar surface, whatever. All of these lines will go through the surface. And therefore, then we use this definition to develop the total flux, electric flux density, which is nothing else but the integral of all of these lines to go through the surface. So practically, you can see it here. We define the total flux as the integral of all of these lines of flux density that goes through the surface, and it's here. And because the surface and the flux density are both vectors, the integral, in fact, is on the inner product between the flux density and the surface, okay? So that integral of the inner product gives us a new scalar function, which we call the total electric flux. Having now introduced flux density and total electric flux, the next thing that we would like to do is to introduce Gauss's law. Gauss demonstrated, first of all, experimentally, and then theoretically, that the divergence of D, where D is the flux density, is equal to rho, all right, or Q, for example. Let me start with a Q, and then eventually we'll go to charge distributions Q. So if you are in a space that has charges all charge is Q. Let's assume each one of them is Q, but distributed everywhere on this volume. And let's assume that one of these is distributed, is located at this point A. All right. And of course, there is the outside volume and that you don't have charges outside. But now, if you go and compute the divergence of D at point A, then this is equal to the charge Q at that point. Let's assume that this Q sub A. Q sub A. And if I go to another point B, where there is no charge, then Gauss's law tells me that the divergence of D at point B is Q sub B, but since there's no Q at point B, is 0. All right, so it's the charge, the diversity of D, the divergence of D is the charge at that point in space, or is 0 if there is no charge there. Now, what is, let's look at this, which is Gauss's law, very critical, very important, Gauss. And let's try to understand really the importance of that. So let's assume that we have a charge Q. And then we are looking at E. Let's assume that we are looking at E along a line, okay? Because this is a 3D chart, so obviously it would give you a 3D field, but now we are looking through a line. We draw this line that goes through the charts. And then we want to show how the field or the divergence, not exactly the divergence, how the field or the electric flux density D vary as we move along the line from the left of the charts to the right of the charts. How is this going to go? The field is going to have a change that goes as 1 over the distance squared. Okay, so as I'm coming closer to the charts, it's going to go like this, and I'm coming away from the, so closer to the charges increases very fast, and away from the charts decreases very fast. And how? If this is the distance, D, in 3D, all right, even if we show it in 1D. In 3D, the E at this point is going to vary as 1 over D squared. As a matter of fact, not equal, and we don't have an equal there, just equal variation. Let me see. It's going to vary as 1 over D squared. Remember this symbol here? That symbol means as. So as. It's going to vary like this. Now, if we take the divergence of D, which is therefore on this point at the Q point Q, right then at that point, then we have that the divergence of E is going to be Q over epsilon. All right. Now, even if E at point Q goes to infinity, around that point Q, E at around point Q, right? At around point Q, E varies as a constant, which is Q over epsilon. So that's what it tells you. So the derivative as you approach the charge of the field is not infinite. Only the field is infinite, but not its derivative. And when the field is infinite, but not the derivative, it means that yes, the field gets to a very high value at that point, infinite. However, the way it changes as it approaches the point is finite. and is equal to the value of the charge. Okay, so just so you understand what the math means, all right? So divergence really give you only the variation of the field around the charge. And if at some point there is no charge, that means that the divergence in that point there is. So if you go really very close to that point, at the change there is minimal, practically zero if there is no charge. The divergence of D is zero if there is no charge. But if there is charge, the divergence of D is equal to the charge. Very important, these observations. Now, from this, therefore, we can now go and say the following. So if I have a charge, which is inside the volume, okay, and if I have all of the feed lines going like that, like this, then from divergence of D equals Q at that point, what we can say is eventually we can prove that the surface integral, which is the total flux through the surface that encloses this volume, and we consider that surface to be like that because it encloses the volume, all right? That's the surface that encloses the volume. Let's call it this. The surface that encloses this volume, and its surface S is this kind of direction. And the surface then is going to be N S, all right? Let me write it separately. The only, so I will write, let me write it here. D then, ds is equal to Q, which means that D is going to be, it means that D is going, that ds, well, that means primarily that the total flux, I'm not going to analyze it more because we're going to write the diversity, we're going to write the divergence theorem. I don't want to analyze it here, but that shows that the total flux around the charge Q is equal to the charge. So the last thing I'm going to do before we start solving problems, all right, next time, because that's what we're going to do on Monday using this theory, is the following. I wanted to introduce the divergence theorem. So the divergence theorem says that if I have this volume, if I take this volume, all right, all of this, and I call that to be volume V, and I have this to be surface S, and the direction of the surface is the normal to this surface. And of course, the direction changes because the surface is spherical. So then what I have as the divergence theorem is the following: the volume integral on this volume B of the divergence of D, all right, on this volume, and the divergence of this scalar is equal to the line integral of D dot ds on the surface, which is enclosing this volume, and this surface as a total surface, as an incremental surface. If we take a small section here, it's going to have the direction N plus a small area as magnitude. Okay, And therefore, from this theorem, which is called the divergence theorem, I can reduce a volume integral to a surface integral. And that's why then I can write this equation and define this surface integral, especially if it's on a closed surface here, as the total flux. And in case of a point charge like this, or some other charges we'll see, but in case it is equal to the charge that is enclosed by the surface. And that is the divergence theorem, which we are going to use to solve problems next time. And we're going to do different types of problems. We're going to solve problems from a line charge first, then we're going to solve a problem from a plane charge, then we're going to solve a problem from a spherical charge. And these are very important because the line charges will give us the electric field out of a charge that is distributed in a line. Plane charges will give us the electric field that we will see inside the capacitor. And volume charges will see the electric field that usually you will see from antennas, all right, eventually. So line charge is the field we will see in transmission lines. Plane charges are the produce fields that we'll see in capacitors. And spherical charges produce fields that we will see in antennas and radiation problems. All right, these are very fun, even if they're statics. The type, how the fields look like is very similar to how we see them in time-varying fields. So that's why it is so fundamental to understand that. So this is the theory, and then on the basis, please review these. And on Monday, we'll devote Monday and Wednesday to solve problems and cover the three cases of line charge, surface charge, and volume charge. Any questions? All right, I will place the recording on the website over the weekend for both cases, since the lecture was online today. Thank you. We have office hours on Sunday if you want to participate. Thank you.